Okay, hello. So we're still on 5.3, which is energy and ecosystems, but this is part 3 of the videos. And today we are looking at this from the specifications, so if you can read this. So we're looking at the net production in plants, which is the top bit, which is the bit that has involved GPP and MPP. And then we're going to look at net production in consumers, and that's the bit at the bottom. So we'll talk about that today. It's an area that comes up quite a lot in questions, so we do need to get our heads around it. And normally students really struggle with this GPP, NPP thing. I never quite understand why, so I expect a lot of questions, and that's fine, but try and read through it first, try and see if you can get your head around it. So these definitions are from the spec, therefore these are the definitions that we are using. So gross primary production is the chemical energy store in a plant biomass. Okay, we do it in a given area of volume in a given time for comparison reasons, but that is your main definition. Net primary production is a chemical energy store in a plant biomass after respiration losses to the environment have been taken into account. So gross primary production is basically everything, okay? Whereas net primary production is everything that plant was able to make through photosynthesis, taking away the glucose that's used in respiration. Because the net primary productivity gives you the chemical energy that is actually available for the rest of the food chain. Gross primary productivity does not necessarily tell us what's available for the rest of the food chain. Okay? And then you've got the bit at the bottom, the net production of consumers, such as animals, can be calculated as N equals I, which is the chemical energy stored in food that's been ingested, minus F plus R. And F is the energy lost to the environment in feces and urine, and R is the respiratory losses to the environment. Okay, so because these have been named, so the top one MPP, GPP minus R, and the N one, because they've been named in the spec, that means they don't have to give it you in the question, which means you do have to know it off by heart. Okay? So let's get our heads around NPP and GPP first. So net primary productivity, so that is what's available to the ecosystem, is gross primary productivity minus respiration. Okay, that's what NPP is. So if you think about it two ways, think about it in this way. The sunlight that falls on the plant does photosynthesis with it, and it produces glucose. That's our GPP, okay? But what we're saying is that not all of that GPP, not all of that glucose that the plant has produced through photosynthesis is available to the next trophic levels in the food chain or in the food web. So why? If you look at the bottom of the screen I'm showing you, you can see there's two possibilities. That glucose that the plant makes during photosynthesis can go two ways. It can either be used in respiration, so it can be used as a respiratory substrate, something that's used in order to generate energy through respiration. So it can either be used, or that glucose could be laid down to make new biomass, like make cellulose or starch or whatever. Okay? Now, if the glucose is burnt in respiration, if it's oxidized in respiration, then that is energy that's not available to the rest of the food chain, because that's gone. Whereas glucose that is used to make biomass, that is energy that's available for the rest of that food chain, because it's made into biological tissue that another organism can come along, eat, digest, absorb, and assimilate and use to make its own biological tissue, and so on and so forth. Okay, does that make sense? I don't know why I'm saying does that make sense, because no one's talking back to me, but there you go. Clearly I'm losing my mind. Right, so GPP is the total amount of chemical energy store that a plant contains before those respiratory losses, whereas NPP is the gross GPP minus respiration. So just go back to, you always use these definitions. Net chemical energy stored in a plant biomass after respiratory losses to the environment has taken place. Okay. So I quite like that diagram. It just makes you think about it. And just to remind you, remember, biomass is not an insignificant thing. It can be a very big thing in some places. You have this graph in your notes, which I think is very useful, because we do have to think about rates of photosynthesis and rates of respiration and how they compare with each other. Because if an organism's rate of photosynthesis is far higher than its rate of respiration, it means it's going to be laying down quite a lot of biomass. Okay, whereas if it's the other way around, if its rate of respiration is higher than the rate of photosynthesis, it's actually using all that glucose not to build biomass, but to go into respiration, which is an energy loss to the environment. Okay, so if you look at what it says, the potato will show an increase in mass, i.e. biomass, between 9 and 23, because net primary productivity, represented by the part of the graph where the rate of photosynthesis is greater than respiration. Okay, so the temperatures outside of that, so below 9 and after 23, respiration rates are higher than photosynthesis. So that net would have eaten into it. Those the respiratory losses will have eaten into that building of biomass. Okay, let's think about it in consumers now. So that's in our plants, net production in consumers. So again, we had a look at this equation. So N is the net production, and that is the same as equal to the chemical energy stored in ingested food minus what's lost in environment of feces and urine and what's lost in respiration. Okay, so I think that's quite straightforward. You might be asked to basically give that equation. You might be probably be asked to use it probably more often. Okay, everyone happy with that? Okay, part 4. Now I've been able to, because I've got a 15-minute limit on this video, but we might as well shove it all together. So this is part 4. So this is for a later lesson. So if this is on Wednesday, the 13th of May, you can stop here. The rest of this will be for Friday, okay? Friday's lesson, which will be the 16th of May, I think. So you can have a look at that then. Okay. Right, I'll continue with this one. So this last little bit of 5.3 says students should be able to appreciate the ways in which productivity is affected by farming practices designed to increase the efficiency of energy transfer by simplifying food webs to reduce energy losses to non-human food chains, reducing respiratory losses within a human food chain. Okay? I think it's self-explanatory. Non-human food chain. I think you understand what that means. Here's a nice picture of a man smelling a leak, just because. Anyway, let's move on. Okay, so we have to think about modern farming methods in comparison to probably more traditional farming methods. And modern farming methods are very different to how it was in the past. Let's have a little look at the comparison between these two kinds of systems, and then we can look at what kind of things that they do to increase efficiency within their farm. So a natural ecosystem, solar energy only, there's no additional energy input, whereas these sort of modern farming methods have solar energy plus what they get from machinery and fossil fuels. Natural ecosystems have a lower productivity, which is much higher in agriculture. But in a natural ecosystem, there is a higher species diversity compared to the modern system. There's more genetic diversity within a species compared to less. Nutrients are recycled naturally within the ecosystem with no addition from the outside, whereas modern farming methods has to use fertilizers because natural recycling is limited because of the fact that we harvest the food for consumption. So therefore we're constantly taking from the soil, we need to add those nutrients back. We will talk about fertilizers and stuff in the next sort of 7.3, I think it is, or 7.4, I can't remember the number. Populations are controlled by natural means such as competition and climate, whereas that's sort of true in naturally agricultural scenarios, but we use pesticides, another thing. And now don't worry about the last one about the climax community, because you don't know about that yet. We will get to that later. Go back to this picture. The reasons why there is a less species diversity and all of those things in modern farming methods is because they tend to do something called monoculture. So they grow the same crop time and time again. And therefore, there's literally only one species of organism there. And therefore, if there's any other insects, it's the insects that would be there would be the insects that like that particular thing. So it's going to reduce the species diversity, which will reduce the bird species diversity, and it has a knock-on effect. Because there's only one type of food source going on. It's sort of linked a little bit to what we did in topic 4. Okay, modern farming methods also do something called intensive rearing as well. So it's this idea that they are going to rear animals in areas where they're going to keep it warm to reduce respiration rates. Because if these animals are having to do a lot of respiration to generate heat to keep warm, then again that's energy lost to their environment, and that means they're not going to put on a lot of mass, which means your chickens aren't going to taste as tasty as they would like to be. So therefore, they tend to keep them in quite warm places. They restrict the movement, again, to reduce respiration. They control the feeding. They make sure that the food is highly digestible, absorbable, and it's going to increase this biomass. They'll exclude predators as well. So they really do a lot of work on it. They also do something called selective breeding, so they can selectively breed an animal so that it will be more efficient at converting food to body mass, or maybe it produces a better yield of milk or something like that. And selective breeding is one of the things that reduces genetic diversity, unfortunately. Okay, let's go to the ethics surrounding this are obviously a bit of an issue. Like I said, reduced genetic diversity is a problem. Rapid spread of diseases in these quite intensive environments is not good. Because they're so crammed in, having to use a lot of antibiotics, which has led to antibiotic resistance. And there's quite a few issues with it, really, I think, with intensive farming. It's not always an ideal scenario. I mean, in terms of effectiveness, efficiency, if we go back to the specification, what it says on here, it says simplifying food webs to reduce energy losses to non-human food chains. So for instance, if you're making a farmer, you've got to make grain to feed your crops, to feed your animals. So I think potentially if that's what they mean by a non-human food chain, a food chain where humans aren't involved in the end consumption. So if they're going to make crops, we are talking about only one trophic level. Reducing the number of trophic levels will reduce the total amount of loss at each level. So therefore, it does become more efficient. But remember that I told you that from sunlight to the first producer is probably one of the most inefficient transfers that there is. But if they can reduce that food chain down to its absolute minimum, they can hopefully increase their efficiency. And then the last one, reducing respiratory losses within a human food chain. So that's just what I've talked about here. This idea of restricting movement, warm environment, controlled feeding, all of this would reduce the respiratory losses, especially number 1 and 2, really. Okay, so that's covered. So the first part of the video was part 3, and this was part 4, really. It's all in the same video, but one part is for your Wednesday lesson and one part's for the Friday lesson. Okay, thank you.